Hi, my name is Zachary Lyons, and today I'll be presenting lab number 4 for Physics 2212 at Georgia Tech, the circuit lab. The goals of this lab were to construct a 2-resistor circuit and measure the current and potential difference over resistors in this circuit using a multimeter. We were then going to analyze the data from this circuit and analyze the relationship between resistance of a resistor and the time for charging and discharging of a capacitor in a resistor-capacitor circuit. The findings of this lab were that the current in the 2-resistor circuit was 0.024 amps, and that the current was constant throughout that circuit. The greater the resistance of a resistor in a resistor-capacitor circuit, the longer the time for a capacitor to charge and discharge. Some key concepts of this lab are the node rule. This states that the current entering a junction will equal the sum of the currents from each junction. This follows the conservation of charge, and it means that the current in equals the current out. The loop rule, another key concept, states that the difference in potential energy, or the potential difference for a round-trip path in a circuit, is zero. This follows the conservation of energy. Another key concept is electrical resistance. The resistance in any component or resistor is equivalent to Ohm's law, assuming that resistance is a constant. This is resistance equals potential difference over the current. When resistors are in parallel, the equivalent resistors of the resistors equals the equation as follows, 1 over the equivalent resistance. When resistors are in series, the equivalent resistance of the resistors equals the sum of all the resistors' resistances. This is the equation for total resistance we will use in this lab. Capacitance measures how much charge can be stored in a capacitor for each unit of potential difference. It is equivalent to the quotient of the charge Q on one of the plates in the capacitor and the absolute value of the potential difference V. The equation is shown here below. A visual model of the resistor circuit that we built in our lab is shown here, with a 47 ohm resistor and a 100 ohm resistor hooked in series with two 1.5 volt batteries. Ammeters were hooked up in series with the circuit. The system was the multimeter that we hooked up to the circuit, and the surroundings were the circuit components, including the currents and potential differences in the circuit. The blue dotted lines in this image show the multimeter measuring voltage between points in the circuit. Here is our resistor circuit that we built in our lab. The calculated current using Ohm's law was found to be 20.40816 milliamps, and the measured current in the circuit by the multimeter was 0.024 amps or 20.4 milliamps, which is very close to our calculations. The potential difference measured at different points in the circuit are shown here. From point A to B, which is on either side of the battery, it was 3 volts. From B to C, it was 0. After the first resistor, it was negative 0.96. After the second resistor, it was negative 2.04, and then the rest of the circuit, 0 volts. This supports the loop rule since the sum of all the potential differences add up to 0. A complete graph of the voltage shown at each point is given here. Our resistor capacitor circuit is shown here to the left. We use two different light bulbs, a 10 ohm light bulb, and then in a separate trial, a 20 ohm light bulb, with one 200 millifaraday capacitor and one 9 volt battery. The circuit is shown up here, and using the equations shown to the right and the resistance and capacitance in the circuit, we were able to find the slope or the time constant of the graph given. That slope was found to be negative 0.167. The relationship between resistance and charging time / discharging time is that the more resistance there was in the resistor, the more time it took for the capacitor to charge and discharge. For the 10 ohm light bulb, it only took 18.63 seconds for it to charge, but for it to discharge, it took 11.6 seconds. For the 20 ohm bulb with more resistance, it took 74.67 seconds to fully charge and 47.93 seconds to fully discharge, which is more than the 10 ohm light bulb. Using Ohm's law, we were able to calculate the current in a two resistor circuit. Some sources of error in the real circuit is that multimeters have some resistance in a real circuit, as well as the wires have some non-zero resistance. The calculations don't include the non-zero resistance from these. The answer to the first what if question is that since the ammeter would have given no resistance in our calculations, the current would have flowed more freely, leading to higher current values at more exact calculations. This is if we were conducting it in an ideal circuit with the ammeter having no resistance. This would lead to higher values for the current and more exact calculations. If there was no resistance and the battery was ideal, meaning there was no resistance in the battery, the circuit would have charged instantly and all of the voltage would go straight to the capacitor. Thank you, guys.